today we'll continue on sparse matrix vector, and if there's time, we can move on to dense graph algorithms. So there have been several, we are currently in the process of checking what is going on with PA2. So please be patient, we'll try to handle it in the coming days. If there are easy cases, I've tried to handle them quickly, but the ones that need to be rerun will take some time to manually investigate, so we are working on it. And other than that, PA3 is ongoing. And if there are any issues with that, please let me know. It's not exactly the same as sparse matrix vector, it's sparse matrix, but a lot of the ideas are related, like the CSR and like the dot product. In some sense, sparse matrix is just many vectors together in the second operand. Yes, so sparse matrix vector. Last time we were talking about, so we had ended on these distributed load balancing or like distributed parallelization techniques for sparse matrix vector. And these are basically so far the same as we have done for the dense case, cutting by rows or cutting by columns. And the last one is cutting by both rows and columns. So if you have both, if you have a large number of processors, and this kind of thing works best if the non-zeros are uniform or close to uniform, because if you just cut it by rows and columns, if the non-zeros are concentrated in one area, for example, let's just pretend like they were all in the upper right corner, then all of these processors would have a lot of work to do, but these would be sitting idle. So that's what load balancing is, and that would be an example of poor load balance, because ideally you would like to get everybody to do some work, if not, and ideally as close to even work as possible. So that is a combination of row and column parallelism, and this sparse matrix vector is in this more recent NAS benchmark for large-scale computers. And yeah, you would get bad load balance if the non-zeros were clustered in any area. So in the sparse case, so previously, like when we had dense matrices, all of this was covered. And so if you cut it by rows and columns, you may have to do this reduction horizontally in the end to get the right value in Y. And in some sense, the ideal case for sparsity is if all the non-zeros are just in this diagonal here, because there would be, if you cut X, just in a review like this, if you had the stream scenario where all of the non-zeros were in this diagonal, you wouldn't need to communicate any entries of X, because this processor would have this part of X, this processor would have this part of X, this processor would have this part of X, this one would have this part, and that would be it. Everybody would have what they would need to compute the end result in Y. And also, there would need to be, and there wouldn't even need to be the horizontal reduction at the end, because normally, if you have the dense case, all of these would be filled, and if you cut it along the columns, then in the end you would have to reduce all these partial results. But if there's nothing here, there's no reduction needed in the very end, and so the final result is just directly computed with no extra communication. And so because ideally we would like to get something close to this, as close as possible, there's an area called reordering algorithms, which you have your matrix, and it has some rows and some columns. Theoretically, you can swap the rows and the column order in any way you would like. Maybe you need to keep a map from your new order to the original order that you can go back and forth. And so if your new order has some structure closer to this, then you can run the algorithm on this more amendable form rather than the original form where the non-zeros may be more spread out. The problem with that, or like the difficulty, is one single sparse matrix vector is often pretty fast, and so the reordering algorithm needs to be relatively low in time, because if your reordering takes 1,000 times the cost of one sparse matrix vector, you need to keep running the sparse matrix vector to catch up the cost. So that's the difficulty there, but it can work. And yeah, so ideally you would like to get non-zeros in the diagonal. Recently, and this one not super recently, but more recent than LinPack, which is one of these original benchmarks for large-scale supercomputers. So LinPack is based on dense linear algebra, and that's how they generate. So twice per year, they run LinPack on many supercomputers, and so there's like a then they make a list called the top 500. And the top 500 is ordered in how fast the machines were able to run them back. So just number one, in terms of flops. So everybody runs the same problem, and you can calculate how fast it took, and then there's some ranking of the supercomputers. And linback is based on dense linear algebra, so it's basically like a dense matrix product. And it's designed to, so linback is dense matrix algebra, which is important, but not representative of all problems. So they introduced a new high-performance conjugate gradient, or HPCG benchmark, which tries to cover a wider variety of problems, including sparse problems, and things that are a bit more challenging than dense matrix algebra, like, for example, stencil computations that we talked about a long time ago when we were talking about caching, or sparse matrix vector, or a global dot product, or even like a vector update. So you have one long vector across the entire supercomputer, and you just want to update the elements in it. And the point of this is, so there's this notion of, it's called computational intensity, and computational intensity is the flops per byte. So for every bit of data that you're reading, how many operations are you doing? And in general, the higher your intensity is, the closer you can get to peak performance, because as we learned in the very beginning, compute is faster than memory. And so, like, if your intensity is low, then you're bottlenecked by memory fetch. If your compute is high, then you're bottlenecked by how fast the compute units can work, which is faster than memory. So the point is that these are lower intensity than the dense linear algebra, which is high intensity. So it's just meant to exercise like a different set of problems. And so this is from a couple years ago, from 2023, the results on HPCG. And they just ran the problems and ranked them, how fast these supercomputers, how fast they can run the different problems. And one interesting thing is that the order that they come in, 1, 2, 3, 4, 5, is different from the order in the top 500. So they put the top 500 rank here. The number 1 in HPCG is the number 4 in top 500. At that time, the number 2 in HPCG was the number 1 in top 500. So it's not so far off. So like, it's not like number 1 in HPCG is like number 100 in the top 500, but different machines are optimized for different things, and so it's not necessarily to be assumed that something that is really good at dense matrix computation will be as good at sparse problems. Another thing to notice, they wrote, so this HPL max is the petaflops per second that the given machine reached on the top 500. So the number 1 is here at that time, which was almost 1,200 petaflops per second on linback. And the number 4 was about 440 flops per second, petaflops per second on the top 500. However, if you look at the petaflops per second in HPCG, it is much, much lower. So this one was 442, this one is 16. This one was almost 1,200, this one is 14. So it is expected that the petaflops or the percent of peak, or the petaflops per second that sparse problems can reach is much lower, because they're bottlenecked more by memory access than by compute time. And peak, so this is fraction of peak. Peak just means when you buy a machine, it tells you it's 3 gigahertz, for example, and it has 4 cores. So the peak on that machine would be 12 gigahertz. It is how many gigahertz can any single core reach, and how many of them we have. So these computers are much bigger than that. They have like thousands of cores maybe, but you can do a similar computation. How many flops can each core do? How many cores do you have? You just multiply. That's like the theoretical peak. You can probably never reach 100%, but for sparse problems, you can reach like only very few percent. Like this is 3. This is less than 1%. Questions? last thing I just said, you can reach only a small fraction of peak for sparse problems. So the next part of this is talking about how to optimize sparse matrix vector for registers and caches, because for sparse problems like sparse matrix vector, the issue is not how many cores you have, or like how many flops theoretically your machine can do per second. It's bottlenecked by the memory access. And so most of the techniques to try to optimize this are trying to optimize the memory access pattern or speed or something. So register blocking, back in around 2005, Rich Riddick and some other folks. So Rich Riddick is another professor here in CSE, and they were working on sparse matrix problems. And they noticed that for some sparse matrices, they have nice structure that is not necessarily captured by just CSR or some of these basic formats. So this one, this matrix, has diagonals, but it's not just any arbitrary diagonals in the whole matrix. Actually, they are in these nice blocked forms. So here, it seems like they're in these 8x8 blocks. They just happen to naturally fall that way. And so they came up with these formats that, so if you store this thing in CSR, it would be like, you would store row 0, and then after that, you would put the non-zeros of row 1, and after that, you put the non-zeros of row 2, and so on. But instead, they changed the format to not necessarily store all the non-zeros of each row in the whole matrix contiguously to each other. That's called register blocking. So, as an example of register blocking, suppose that we have this matrix, and this is just in the original CSR form that we talked about last time. For sparse matrix vector, like we were talking earlier, the bottleneck is memory access time, not compute access time. And so the point of these block formats is to try to reduce the cost to access the matrix for memory. In sparse matrix vector, for every non-zero, you have to only do 2 flops. You do like the multiplication with x, and you do the addition into the output. However, to fetch that entry, you have to get 1 column ID, because you need to figure out which ID of x it is, or which ID corresponds in x, and also the float value for just the value part. So you multiply the value part, but to access the correct index, you have to access the explicitly written index in call ID. And so that's plain CSR. And in block compressed row, or BCSR, the idea is rather than storing each non-zero, you cut the unit, or like the minimum unit is no longer 1 single non-zero, but a block of non-zeros. And the block size is fixed up front. In this example, it's 2x2. And you cut the matrix just in 2x2 pieces. Like here, each of these is also 2x2, but they're empty. So we don't represent them. And any non-empty block, even if it has at least 1 single non-zero in that block, then it is represented in block compressed row. And when you store these blocks, you may not get something so perfect like what we just saw earlier, where everything fits nicely into 8x8. In this example, with this 2x2 block size, there are some empty spaces within the blocks, and there you would represent the explicit zeros. And that is called fill-in, because normally in CSR you would never represent any zeros. So there's some slight, sometimes depending on the block size, space trade-off for block formats, because it's unlikely that any matrix will fit perfectly into some block size. And then the reason for this is that the time to fetch the matrix for memory decreases because you take advantage of prefetching. And so you take advantage of prefetching in the blocks and the cache line size. So normally in your machine, the cache line size is 64 bytes. And so when you read 64 bytes, ideally you would like that to contain useful data. In reality, if you run experiments, so if your memory block size was only 64 and it was equally as good to access any 64 bytes arbitrarily, then there would be no benefit between reading, say, 64, 64, or 64 right next to each other. But if you actually do run experiments in your machine, you'll find that it is faster to read 128 contiguous bytes than 64 here and 64 far somewhere else. And the reason is because in your machine, because that's such a common access pattern to just go like left to right in array or something, there's something called prefetcher which tries to hide the latency and starts and loads up the memory access even before you move on from this cache line. So that is the high-level reasoning behind why this blocking format also is useful. Yeah, and the blocking format depends on the block size. So this one is parameterized by 4 by 4, and it's the same matrix, but now it's cut into 4 by 4 pieces, and so it has 3 non-empty blocks and 1 empty block. And the way you store that is here. So the high-level idea is similar to CSR, but now the minimum unit is the 2 by 2 block here rather than the single element. And the column index is given by like, when you cut the whole matrix into blocks, each block has a block row and block column. So this would be 0, 0. This would be 1, 1. So that's the same. That's the given column index, and the row pointer is the same. It has the same meaning as in CSR, as the offset. So one of the main questions that this idea raises is how do you choose the correct block size? And it seems like it should be dependent. It kind of like intuitively feels like it should depend on the matrix because, like in the example we saw earlier, it feels like 8 by 8 just perfectly fit those blocks, so that would be a natural choice for size. But actually, even on that one, even on this matrix where everything fits perfectly in 8 by 8 blocks, by doing some testing, 8 by 8 on different machines, 8 by 8 is the best on only one of the machines they tested. In this example, I think like 6. And the way to read this is the block size here, 1 by 1, 2 by 1, 4 by 1, 8 by 1. So yeah, this is the row block size, this is the column block size, so this is like 2 by 4. And the number is the speed up, and all is normalized to 1. The block size 1 is basically the same. And so for this one, the best was 4 by 1. For this one, the best is 4 by 2. There's 4 more machines. This one, the best is 8 by 8. This one is 4 by 4, 4 by 1, and 2 by 8. So not only does it depend on so the matrix is the same throughout the entire thing. And this is just changing the different machines. So not only does it depend on the matrix, it also depends on the machine. Another issue is that not everything fits in perfect 8 by 8 blocks, or in general, R by C blocks. So this one, this other matrix, if you look at the structure, there's not really any block size that can, besides 1 by 1, that would perfectly fit everything. Because you have these empty gaps here. One thing that looks okay, you can try 3 by 3. And with 3 by 3, like it kind of works in that many of the blocks are empty. So you would like, ideally, many of the blocks to be empty, and the ones that you have, you would like them to be mostly full, because otherwise you have to spend a lot of extra space to explicitly store the non-zeros. So the point of the one high-level idea behind the block format is that if by adding these explicit zeros, you add space and potentially even add computations. Like with CSR, you never have to do any zero computations because the only entries that are stored there are zeros, or are not zeros, sorry. But with block formats, sometimes you explicitly store zeros. And if you just directly read all the all the entries in the block and do the relevant computations, some of those will be zeros. But it turns out that that is actually okay. And the reason is because of this discrepancy between compute and memory speed. So you pay sometimes a little bit in compute time, but you get overall speed up because you have saved in memory access time. So memory access time by taking advantage of contiguous access, and also you can write very tight loops. Like if the block size is fixed, you can just unroll the loop on this entire 3x3 thing. And so it just becomes a very tight kernel. You can write every single access in a straight line. So it is technically more work in the sense that you do more operations, but sometimes it does lead to speed up. Like on this matrix, they tested on this Pentium 3 machine, and they found that it got 1.5x faster in this blocking. Yes, please go ahead. Yes, good question. So some matrix where you may see block structures like grid problems, for example, or sometimes this one is from fluid dynamics. So this has this particular structure. I know that some matrices with block structure, they can come from finite element method simulation or chemistry simulation as well. But between the different applications, the block structure also looks different. Yeah, so I know this is a little bit far from like the things that we have been doing in the sense that it's not like doing latency bandwidth calculation and so on, but I think it's interesting because it provides this example of like how you do this actual trying to optimize for these structures and balance these actual issues of like memory access versus computation in problems that are not so nice as this matrix multiply. So it's a nice example of performance engineering. So they have these matrices, or libraries for sparse matrices, but they're kind of hard to build because there's so many possible formats for sparse matrices. For dense matrix, it's easy, it's like an idiosyncratic matrix. But sparse matrix, we have learned at least several possible formats already. And so libraries, they're well-known libraries like PETC, which really knows these are popular libraries, but they let the user provide the format. And then, as we know, depending on the format, the way that you implement the sparse matrix vector looks different as well, because you have to do the iteration differently. Like between CSR and block CSR, the inner loops looks different. And another one, yeah, so when you want to, if you're trying to optimize a single sparse matrix vector iteration, like one single instance of sparse matrix vector, optimization can mostly only depend on the non-zero structure. And it can also mostly only depend on the optimizing the memory access. And back then, they tried to, I think this is about from 2005, but they introduced this library called OSCI, which is Optimized Sparse Kernel Interface, which is a library that implements some of these block formats. So in the block formats, we were talking about choosing block sizes and how it's not obvious. Even if you have full knowledge of the matrix, it depends also on the machine, how you should choose the block size. And in 2001, they introduced this notion of the fill. And the fill for an n-dimensional tensor, this example is just for a two-dimensional tensor or a matrix. It's parameterized by the number of non-zeros in the matrix, the blocking, so you have to choose the block size in 2D, just row size, column size, and the number of non-empty blocks as a result of the blocking. So that is a result of the block size that is chosen and also the non-zero structure. In this picture, the squares are non-zeros and the circles are zeros that were filled in. And the fill is just the volume of the block, so this is B1, B2, times up to Bn, times the number of blocks, divided by the total number of non-zeros originally. So this thing on the top is how many elements were stored under the block format. And this thing on the bottom is what is the minimum number of elements that you would have had to store, because that's the number of non-zeros. And the ratio is the overall space overhead that was introduced due to blocking. So in this example, there's 14 non-empty blocks. The block size is 2 by 3, so 2 rows, 1, 2, 3 columns. So the volume is 6 in each block. The number of blocks is 14. The total number of non-zeros is 36, and the total overhead is about 2.3 times. And the meaning of this is if it's higher, the blocking wastes more space. If it's lower, so the minimum is 1, because this thing is minimized at 1 by 1 blocks, which is just CSR. And high level, they tried to use this. So the reason that we're interested in computing the fill, or actually in reality they don't compute it, they try to estimate it because you need to do it over all the blocks, is to try to plug it into some kind of performance model. So from an empirical standpoint, there's some relationship between how much empty space is used and the performance, because ideally you would like to try to lower the amount of empty space. In some sense, the fill is a measure of the blocking quality, or how well whatever block size adapts to the matrix shape. But of course, it's not enough just to minimize it, because you would just choose 1 by 1 and be done with it. So the performance model is trying to use the fill and other information to map some blocking to some expected performance in flux. So this is like an early auto-tuning pipeline for a sparse matrix vector. And the input is given a matrix to compute a table of fills, either exactly or approximation, over all possible blockings. So it's easier if you only were interested in one of the blockings, like 2 by 2 or 4 by 4 or something. But actually you want all of them, usually up to 16 by 16, to choose what is the correct form. You plug it into this performance model on a given machine. And ideally you would like to get out the expected performance of blocked sparse matrix vector over all possible blockings. Then you would choose the max over this one to choose which block size to use. Questions? Back in Richard Wood's thesis, they introduced this performance model. I'm going to call it the sparsity performance model. And what happens is you have a machine, and you compute some performance profile of the machine based on blocking. And the way that you generate this performance profile is independent of any sparse matrix operation so far. You just take a dense matrix, you store it in the block format, and you run matrix vector. And that gives you some flops. And so that, in some sense, is a measure of how good a given blocking is on that machine, independent of the sparsity structure for a second. Because the actual inner loop would be the same, it just depends on the block size. And like I said earlier, you can even unroll that for lower overhead. And so they generate this performance matrix, which is a 16 by 16 matrix of how many flops you can get for a dense matrix multiply given a block size. The table of fills, which is something that is computed per sparse matrix, is plugged into this performance model, and out comes the expected performance of the sparse matrix vector on that particular sparse matrix over all possible blockings. So this thing is in flops. This is the fill. So in some sense, higher fill is worse. It's just higher space overhead, and higher performance is better because flops up is good. So this is just an estimate, but you have to choose something. Performance modeling is quite hard, I think, because there's a lot of stuff going on, and it's really hard to account for all of them. And there's also trade-off between like the granularity of the performance model and the accuracy, because if you try to model something or simulate it to a very fine granularity, it will take a long time. And so you don't want to have this performance model take like 1 million times the cost of your matrix vector product. So this is something that is simple to calculate. This performance profile just needs to calculate once per machine. And this table of fills, it turns out that it's fast to estimate with good accuracy. And so this is really hard to mathematically prove. I don't think that it's possible to mathematically prove that you can always get within some factor of peak performance, or the best performance, not peak performance, like the best performance possible, given a block size, but they showed empirically that if you know the fill exactly, the performance of the given blocking scheme chosen by that fill is optimal or near optimal within 5%. So this is just experimental, and the way that you can show that is you have a matrix, you run the sparse matrix vector with all possible block sizes, and you know how long it takes. And one of them will be the fastest. And then one of them, potentially a different one, will be chosen if you know the exact fill matrix using this performance profile. Turns out that if you choose it according to this performance profile, given exact knowledge of the fill, they would line up with the best one or close to the best one. Yes.
So are these like used on the fly, doing something or is this just for the profile itself?
Which part do you mean? So it's a good question. The question was like, is this something that you would actually use, like to optimize the sparse matrix vector product, or is something just to understand like the underlying architecture of the machine? This performance profile, I think, this thing is dependent only on the architecture of the machine, pretty much, because you compute it once upfront independently of any sparse matrix product. This whole performance model, which includes this upfront matrix and the fills, can be used in scientific computing auto-tuning pipelines. So the flow would be like, you get a new sparse matrix, you estimate the table of fills, you have computed this upfront at some point, and you plug them together, and you get now an estimate of which one would have the highest flops. It may not be perfect, but through some experimental validation, they show that it's usually pretty good or close to pretty good. Yes, this perf B is generated by, you take a dense matrix, you store it in the block format, given whatever blocking, it's a matrix of different blockings, and you just run it, and you calculate how many flops you get. It would probably be minimized at 1 by 1, because for dense matrices, that just introduces the overhead of the explicit polynomials with no use of the calculator. Yes.
Is it cheap to calculate the table of fills for all the blockings?
It's a very good question. It is expensive to calculate it exactly. It is, in the original paper, they estimated it through some heuristics, like they sampled block rows, and they calculated the fills there, and it was pretty cheap. At this point, not a couple of years ago, during my PhD, I wrote a paper on how to do sampling with guarantees by sampling the non-zeros rather than sampling the block rows, and that you can do pretty fast.
So when you approximate the fill, is it still optimal or near optimal, or does that one hold exactly how?
So yeah, good point. If you estimate the fill, you may not get it exactly, but you can prove that you can get it within some error bound. And then from there, then you need to plug it into this performance model and then show that the estimate is actually still gives you some okay results. It turns out that it still does. Yeah. Estimating, like even if you can prove a bound on the fill estimation, doesn't necessarily prove a bound on the downstream performance. Because this part of like the connection between the fill and the flops is not like a mathematical thing. Yeah, it's a good question. Maybe the short answer is we can do it. We can do it quickly with some work. It's just an example of what this. It's called a register profile, actually, what it looks like. So from 1 by 1 up to 12 by 12. It's minimized, or it's all normalized to the 1 by 1. And red means better, blue is worse. And so on this machine, it was, I think the best one is like around here, 7 by 1. Or actually, no, here, this is 4 by 2. This thing, I think you just kind of have to run it like to analytically figure this out front. It depends on the machine parameters. Yeah, and it's in flops. So this, at that time, it was in mega flops. So we would generate this one time per machine. You can use it across all sparse matrices that are input into the machine. I guess another optimization is like if you want to multiply the same sparse matrix on different machines, you could reuse the table of fill estimations also, because the fill doesn't change, it just depends on the matrix and the blocking. So if you want to save it, you can. Yeah. And this is how they look on the different machines. So the actual numbers are not super important at this point, but the point is that they look different depending on the machine. And so running it once on one machine does not tell you anything about how it will look on another one. Yeah, and this is just some standard results. So blue circle is the best. So the y-axis is the performance in terms of megaflops per second. The x-axis is different matrices indexed by the number that they were in this evaluation. And the categories like this FEM is finite element method. This LP is linear program. This is other. So we tried to group them by where they came from. The reference is 1 by 1. And the red left triangle is what you get if you compute the exact fill. And this green and purple is some heuristic to estimate the fill. And yeah, so the lowest one, this star looking thing, is the reference of 1 by 1 blocking, which is just CSR. This blue block is what is the best that you can possibly achieve over all blockings. And in most cases, this red triangle is at, I think it's sometimes hiding under this blue thing. Because, like, for example, if you just look at the first column, the red triangle doesn't show up. So I think it's probably just hiding here. And the green square, which is a fill estimation, is very close to the blue one. Very close to the blue circle in many cases. Like here, this one, they line up. In all of these, they also line up. And yeah, this is the fraction of peak. So normally, with no observation, the percentage of peak on this machine is maybe between 5 and 8%. And then with register blocking, you can go up in some extreme case to even over like 53%. So that is register blocking, and register blocking is usually, the blocks are very small, usually they're limited to about 12 by 12. There's another higher level blocking, which is called cache blocking. So registers are like, you have very small fixed number of registers in your machine, and cache blocking, caches are much bigger than the number of registers that you have. Registers are usually like on the order of 10, maybe, or so, and cache blocking, depending on the level, it can be in the order of like kilobytes or megabytes. And so for in CSR, to compute the dot product on every row, and that gives you the entire sparse matrix vector, there's some reuse opportunity in the X vector. So reuse is when you have some data, reuse just means how, if you go back through it. And the reason that we would have caches, the reason for caches is because sometimes we use existing programs. Because there's no point in caches if you only access everything once. Because caches allow fast access to repeated data. So reuse and caches are highly related because if you have no reuse, then there's no point in your cache. But the higher your reuse, the better use you can make of the cache. And so the amount of reuse, or which part of the data you have reuse in, depends on the algorithm or the problem. So for sparse matrix vector, there's no reuse in the matrix. We touch every non-zero once. But there is reuse in the vectors, both x and y, the input and the output. Because you may touch the same value in the input vector x many times. And then also for y, you keep accumulating the same entry in the output. So for matrices, in the x vector, if you have a matrix that has basically all the non-zeros clustered in the diagonal, you would have very good reuse of the vector because all the entries around each other would be accessing the same elements in the vector. And so for cache blocking, it's just blocking, but the blocks are much bigger. So rather than 12 by 12, if you look at these block sizes, now it's log 2 of starting from 6 and going to 16. And here again is log 2 from 5 to 15. So this is row size, this is column size. So it's the same idea of blocking, but just with much bigger blocks. The reason for that is you try to get the blocks to fit into the cache. And they did some, again, this profile, the baseline at just probably regular CSR is 44 megaflops per second. And at 16K by 16K blocks, they get up to 210 megaflops per second on this particular matrix. Any questions? Yes?
So we're interested about forms, which we wanted more efficient register level, we wanted more efficient
Good question. Theoretically, you could use both. Within each register, within each cache block, you could store that. So you can think of each cache block as a matrix or submatrix, and you can store that in the register block format as well. So theoretically, they can compose like that, and maybe you can get benefits for. Maybe you can get benefits in both ways. I would say that usually register block. Well, both of them are targeted towards different use cases. Like register blocking is for when you have matrices with these small blocks with the non-zeros, and cache blocking is if you have matrices with larger blocks of more dense parts, like here, the 16K by 16K. Any questions? Yes.
How are the limits to the block size determined? Is it just by the architecture that the maximum is set?
Yeah, good. How are the limits to the block size? Like, why is the max like 12 by 12 or something? Yeah, it probably depends on the architecture. It depends on how many. Yeah, it depends on how many registers you have. It depends on the size of L1. For the caches, it probably depends on the size of L1 and L2. So on. For the registers, there's an L0 as well. Another thing is that the bigger bigger your allowed block size, the more fields you have to compute. So maybe they also try to balance that. So the last part of this is just to show a little bit of data about what these look like. So this is on 4 different machines: Xeon, Opteron, this UltraSpark, and Subblade. They're a bit old. I looked it up. They have 4 cores or so each. So nowadays 4 cores is not much, but the high level idea still stands. And so they just did some tuning for sparse matrix vector. And the pink line is just naive sparse matrix vector, like the serial code that we looked at last time of a couple of loops over CSR. And the gray line is the naive parallelization, which is you just put a parallel 4 over the rows. So if you remember, there are 2 4s. One outer one is over the rows, the inner one is over the column IDs in CSR. And so you can trivially parallelize over the rows, because those all accumulate into different entries in Y. And the y-axis is gigaflops per second, the x-axis is different matrices. The leftmost one is dense, but the other ones are sparse. And these are different machines, like they have different. The y-axis is always the same in terms of range, but the speedups and the absolute times are very different. Like here, you can see the pink one is all the way down there in these 2 cases, but here the pink one is not bad. It's kind of like above, around 0.5 gigaflops per second. But however, the speedup is not so good on these because you have 4 cores, and in most cases the speedup is maybe 2 or less, maybe between 2 and 3 in this case. But here, like it's mostly 2, I would say. The pink is about 0.5, the gray goes to about 1 in most of the cases. So just sticking the parallel 4 does not achieve, the best you could possibly do in speedup is the 4, so that's why I put it up to 4. It does not achieve close to the maximum speedup in these cases. This one, maybe just like the serial version is so bad that the speedup is really good. But this one, like, the serial version is very bad, and the speedup is also nothing. So parallel scaling is not good. And this is like a common, one common technique in when you actually try to optimize codes that you will see when you are doing the homework is sometimes you have performance issues or scalability, parallel scalability issues. And the issue is not how many threads you have or how many ranks you have. The issue is the communication or the memory access time. And so sometimes it feels a little bit counterintuitive because like it feels like if you're not getting good parallel scaling, then maybe the issue is in the parallelization or in the available parallel work. But actually often, if you have issues with parallel scaling, the issue is memory bandwidth rather than how much. Because like available parallel work in SpMV is quite high. It's parallelized over the rows. The number of rows is maybe on the order of 10,000 times to 1 million, and the amount of cores is 4. So there's no issue with the parallelization in the work. I was saying that because it's also related to the programming assignment. If you have issues in timing, it may not be an issue of how you split the parallel work. It may be an issue of how memory friendly is your inner kernel or local matrix multiplication. And you can find that out by timing different parts, like timing the computation part, timing the communication part, and seeing which one is the bottleneck. So after parallelism, we didn't do a whole lot to do the parallelism, we just stuck the parallel 4 on the outer loop. The only optimization after that is to try to minimize the memory traffic. So we did register blocking, you can compress the CSR even further using something like delta compression, and you can also, so that's smaller indices. You can use other formats, like block formats. You can use smaller indices, like try to compress the column IDs. And so this yellow this blue-ish one, NUMA, this greenish one, they kind of look similar, prefetching, and the yellow one is compression. So this top, they go from bottom to top. So this is parallel. NUMA didn't really show up in most of these. This is prefetch, this is compression. So there is more speed up to be had using compression and memory techniques. And these are not bounded by, the improvements, they're no longer bounded by like P. So with parallelization alone, the possible speed up that you can get if you have P cores or threads or processors is P. But if you have memory blocking, like this, or if you have memory optimizations, the speed up is not bounded by parallelism. Another thing is that the matrix, the benefit that we get depends on the matrix. So some matrices achieve a lot of speed up from the techniques, some of them achieve pretty little speed up. So it depends on how well the technique can fit to the structure. And it's register blocking, there's cache and TLB blocking. And this is, so this whole pipeline is called auto-tuning because it's trying to automate the process, like this whole thing about finding the fill, finding the correct blocking. That whole thing is ideally automated away, like you don't have to manually look at the block size, the selection of the block size using the using the techniques that we just said. The selection of the block size is automated. The conversion into block format is automated. So that's auto-tuning. You don't have to manually choose any of the parameters. So this is the performance once you fully auto-tune the sparse matrix vector. And why does it work sometimes better than others? Depends on the matrix structure, and it also depends on the machine. So cache blocking, for example, may work better if your cache is bigger. Like you can get a bigger block. And we saw, like in that one profile, cache profile, that the best one in that example was 16 by 16K, 16K by 16K, which is pretty big. And another one on the matrix side is register blocking is better when your matrix is in this block, when the non-zeros are clumped together in blocks. So the benefit of the register blocking depends on the structure of the matrix as well. This is just the max speed up that was gotten on different architectures. So this one was 2.7, this one was 35 times. So really depends on your machine as well. This is the last part. So the second half was about tuning. Most of the stuff that we talked today was about auto-tuning. And the high level is that both writing sparse matrix kernels and tuning the sparse matrix kernels is harder than the dense ones, because for dense it's pretty straightforward. You store it in the adjacency matrix form and you run some sort of blocking. But for sparse it's harder because you have to choose which block size and which level is blocking, like register or cache blocking. And for sparse matrix vector it's also harder to get the speed up, like parallel speed up, because the computational intensity is lower. So the whole thing's bottlenecked by the time to read the matrix, because you have to read 2 elements per entry. You have to read the column ID and you have to read the value. Whereas in the dense world, you only have to read the value, because the index is implicit in just in the position. And so that lowers the intensity, because intensity is how many useful operations, like how many flops you're doing per byte. And so in the dense computations, the number of flops per byte is higher, so the intensity is higher. And register blocking and other forms of compression can increase the speed up as well. Cache blocking can help, but less so. And for distributed memory and also for shared memory, reordering can help, because you try to order things along the main diagonal. Auto-tuning is possible. It depends on the sparsing structure, and it depends on the sparsing structure. Like if something is very uniformly the non-zeros are very uniformly spread out, it's unlikely that blocking will help. And ideally, yeah, after tuning, this thing will still be memory bandwidth limited, but it should be bandwidth limited rather than latency limited. And then one thing that I didn't talk about today, but is a very rich area of work, is that this whole thing is about optimizing one single instance of a sparse matrix vector. But you can usually, in solvers, for example, you run many instances of sparse matrix vector, like you try to run it until convergence to something. And so maybe you can optimize also at a higher level, like across the iterations. There may be some optimizations, like you can reduce the number of iterations and get to convergence faster. But that is something higher level and depends on the bigger pipeline. Questions? If there are no questions, we can do graph algorithms for a little bit. So, I think I can finish, but we have about 15 minutes, and we can talk a little bit, and we can continue next time. So, the next part is about graph algorithms. And this part is not really, I wouldn't say it's anything new compared to the stuff that we've already learned. It uses a lot of the dense matrix algorithms that we have learned so far, like Canon's algorithm or matrix multiplication, and it's just showing how to use them in different kinds of problems. So a graph is a high-level abstraction, which is two things. It contains a set of vertices and a set of edges. The vertices are entities, and the edges are connections between entities. And graphs are this really powerful abstraction in computing because they allow you to represent relationships between the data. And sometimes you can augment the vertices and edges with other data, like weights. Like in a road network, for example, the weights may represent how much traffic there is along certain lines. Or in a social network, the weight could be like how strong is this connection, like how many times do these people interact. There are a bunch of different types of graphs. So you can represent the graph as this tuple of two sets, V and E, which is vertices and edges. And E is in V cross V. So V cross V is like a set of tuples that is equal to size of V squared. And edge is just a subset of all possible edges. And a directed graph means that the tuples have directionality, which means that if you have a tuple U to V, there's not necessarily the corresponding tuple V to U. And multigraph, you can have multiple edges between the same pair of nodes, and then the other side of the directed graph is undirected graph, where if you have an edge from U to V, then you have one also V to U. And the hypergraph is a general form of graph that edges can connect more than two vertices. So instead of V cross V, it would like V to some arbitrary power, and every edge is now a set rather than a tuple. But we're just going to be doing regular graphs, not hypergraphs. We don't need to spend too much time on this. We have spent a lot of time talking about representations. So any dense matrix or sparse matrix representation can also be used for graphs because there's this duality between graphs and matrices, and if you have like an n by n where n is equal to the number of vertices, then you can represent the adjacencies of the graph using the matrix entries. So the most basic way is the adjacency matrix. Its size, if you have n vertices, the matrix is of size n by n, and you put a 1 where there's a connection, and 0 if there's no connection. And in the weighted case, you can put some weights rather than 1 on that edge. And if it's undirected, then the adjacency matrix is symmetric across the main diagonal. Because, like, UV and VU are both there. There are many possible there's as many graph representations as matrix representations. And possibly more because there's hypergraphs. So adjacency matrix has space V squared, or cardinality of V squared. The incidence matrix, rather than the rows are the vertices, and the columns are not vertices but edges. So there are E possible edges, and the numbers in the columns mark which vertices are at those edges. So E0 connects vertex 0 with vertex 2. And E1 connects vertex 1 with vertex 2. So there's not that much reason to use this for regular graphs as opposed to the adjacency matrix, but this works well in hypergraphs because there may be more than 2 entries per column in hypergraphs. Then these sparser representations, adjacency list takes space V plus E, CSR and CSC, which is the column form, also take space proportional to V plus E. And for sparse graphs, E is usually much less than V squared. And so for sparse graphs, we prefer these representations because they can save a lot of space. Questions? So in this part, we're just going to be doing parallel algorithms for dense graphs, which is a simpler case than for sparse graphs, but still interesting because you get to use the matrix algorithms. So we can assume that we have a dense weighted graph. So we're going to store it, and we're going to store it in adjacency matrix form. And we'll also assume that we have a large number of vertices that can be spread across many processors. And the way the flow of this will work is first we will just go through the sequential algorithm, and then a distributed memory parallel version using the adjacency matrix. Then we're going to go through these algorithms. So these are algorithms that you would learn in an undergraduate algorithms class. Minimum spanning tree, Prim's algorithm is a very famous algorithm for MST, single source shortest paths, 3-Dijkstra's algorithm, and all-pair shortest paths. People already know these algorithms? Or like, is it like you know them but it's been a while? So for today, probably we can just go through Prim's algorithm. A spanning tree on an underactive graph G is a subgraph that is a tree containing all the vertices of G. And a tree is just a connected acyclic graph. So in a tree, the number of edges is pretty much the number of vertices. 1, 2, 3, 4, 5 vertices. 1, 2. So if you have n vertices, the tree has n minus 1 edges. 1, 2, 3, 4. And in a weighted graph, the weight of the subgraph is equal to the sum of the weights on all the edges in that subgraph. And a minimum spanning tree for a weighted underactive graph is the spanning tree with minimum weight. So the spanning tree has to contain all the vertices. And the edges contain the weights, so we're trying to generate a spanning tree with minimum weight on the edges. So Prim's algorithm is a classical greedy algorithm for MST. It's this iterative algorithm. You start with an arbitrary vertex, and you just grow the tree incrementally. So you start with a vertex, which is the start of the MST. Then from that vertex, you look at all the edges, and you pick the minimum distance one, and you add whatever is the endpoint into the MST. And then now you have an MST of 2 vertices. Now you need to add the third vertex. So the 2 vertices that are there are connected to some other vertices. Now you find the one that's minimum distance from your current tree, and you add it in. And you keep going until you have reached all the vertices. Questions? So this is an illustration of how this works. Say we have this graph, A, B, C, D, E, F, and there's some edges, and the edges have some weights. And this is the adjacency matrix representation of that graph. So the edge from A to anything to anything, or anything to itself, is just 0. And then here we have from A to B is 1. A to B. And infinity means that they're not connected, or not connected directly. So for Prim's algorithm, we start with arbitrarily that B is the first vertex in the spanning tree. So the first step is you take the adjacency of B and you copy it into the distance vector. And this distance vector is going to store the minimum distance between our current spanning tree and all the other vertices. So the length of the distance vector is equal to the number of vertices. And in the beginning, it just contains the adjacencies of the one vertex that we have so far in the spanning tree. And so you look, so this is the first step, and then after this, now we look at the adjacencies from the current spanning tree, and we pick what is the minimum one, what is the closest one to us from the current spanning tree. We can break ties arbitrarily, so here A and D are both equally close to B, but I'm just going to pick A arbitrarily, and so now we add, we pick D arbitrarily actually, this one. And so now we have B and D in the spanning tree. And we need to update this distance vector based on the adjacencies of D, because now more stuff will have gotten closer to the spanning tree. And the way that we update this is you take the adjacencies of D, and you take the element-wise min between this row and this vector, because this is the distance between, these are all the edges connected to D, and these are the distances between the current spanning tree and anywhere else in the graph. And so, like, adding a new vertex into the spanning tree can only decrease the distances between what is in the spanning tree and anything outside of it. Then we just keep repeating that. So next we would add A, because A has the minimum distance. And finally, this is our spanning tree. Questions? So there are 2 main steps in this algorithm. There's n overall steps, where n is the number of vertices you have. And the 2 parts in each step are, 1, you have to choose the next vertex to add into the tree. And then 2, you have to update the distance vector based on what you have added. This is the pseudocode for the serial version of Prim's algorithm. So this part, in the beginning, is just initialization. You pick some starting vertex R. V sub t is the vertices that are currently in the spanning tree. Starts with R, which is some vertex. The distance vector of R is equal to 0, because R is in distance vector. And for all vertices that are not currently in the spanning tree, if an edge from R to B exists, then you set the distance as the weight from R to B. Because currently R is the only thing in the spanning tree. Otherwise, you set to infinity because they're not adjacent. So that's just the initialization. And then this is the main this is the main loop. So while the spanning tree's vertices are not equal to the whole set of vertices, the first step is you have to take the min over the distance vector to find what is the closest thing to the current tree. Now you add it into the set of vertices, and for all other vertices, you do this relaxation. So the distance vector is, you update the distance vector equal to the min of what is currently in the distance vector and the weight from U to V, where U is the thing that just got added to the spanning tree. Which parts are easy to parallelize? This one. Yeah. Yeah, I mean this one too, but this is initialization. So the parts that are easy to parallelize is taking the min over the distance vector, and also taking the min with the distance vector compared to this one row in the identity matrix. Okay, questions on that? Yeah, and this is just the picture of how you would split it up across the processes. So you have P processors, this is the adjacency matrix, and we can split the adjacency matrix column-wise. So this is processor 0, this is processor 1, so on, up to processor P minus 1. The distance vector, processor 0, processor 1, up to P minus 1. And so in each round, we select one new thing to add from here, and that corresponds to some row here. And then we take the min of, like, say we chose, just pretend we chose this row, we take the min of this part, and this part, element-wise. So the whole thing doesn't require any communication in the rounds. Or, sorry, this min part doesn't require communication. The finding the new thing takes some communication because this is split across the processors. And we will continue next round. So think about it then.